Firearm suppressors are devices used to reduce the sound of firearm discharges, and work by trapping the rapidly expanding gases exiting the muzzle of a firearm in a series of chambers that allow the gas to expand and cool before exiting the firearm. Without a suppressor, these gases rapidly expand from the muzzle once the bullet exits the barrel, producing a sound that can be anywhere from 140 to 190 decibels in magnitude depending on the firearm. With a well-designed suppressor, however, this noise level can be reduced significantly, often to OSHA-defined hearing-safe levels. The following example shows how a suppressor can change the sound of a firearm discharge. In order to investigate the effectiveness of a Gemtech GMT300BLK suppressor, which is a unique monocore suppressor that utilizes a proprietary baffle design which claims to reduce the discharge noise of a firearm chambered in 300 blackout by 36 to 39 decibels, a CFD model was created in ANSYS Fluent to simulate the transient state, three-dimensional flow through the suppressor during the discharge of a subsonic 300 blackout round. For simplicity, it was assumed that the working fluid in the suppressor would be air that is initially at room temperature, and due to computational resource and software constraints, the bullet that would be traveling through the suppressor during a discharge was omitted from the problem. To solve this problem, a model of the internal volume of the suppressor was created in SolidWorks from a model of the suppressor, and imported into ANSYS to be meshed and analyzed. In order to obtain the time-dependent mass flow rate inlet condition prescribed to the barrel outlet into the suppressor, the U.S. Army's Engineering Design Handbook for Gun Muzzle Devices was consulted to obtain the mass flow rate equation for gases leaving the muzzle of a firearm after the bullet has left the barrel. It was assumed that the 300 blackout round was loaded with a 210-grain bullet and 11.8 grains of powder and fired from the 10-inch barrel with 1-in-7 rifling. From test data obtained from this load, it was assumed that the muzzle velocity of this bullet would be 1,137 feet per second. It was also assumed that the barrel was perfectly circular and that no chamber or rifling was present in the volume and bore area calculations. The following mass flow rate profile was obtained from the calculated and prescribed system properties and the mass flow rate equation. An equation was fit to this profile, and written into a user-defined function for use in the model. The outflow surfaces were assumed to be at zero-gauge pressure, as the gases are being released into the environment once they exit the suppressor. At all walls in the suppressor, it was assumed that a no-slip condition exists. Because this problem involves high-speed flow of a compressible gas, the density-based solver was chosen for this problem. Additionally, to simulate viscous effects and enable turbulence modeling, the realizable K-epsilon model was chosen for this problem because of its robustness, reasonable accuracy, and computational efficiency for turbulent flow problems. The solver was said to run for a total of 2,000 time steps, each of which was fixed to a microsecond in duration, for a total simulation time of 2 milliseconds. The solver was said to run 15 iterations per time step to both ensure that a converged solution was reached and that computation time was not excessive. When the results are viewed, it is observed that the suppressor effectively expands and slows the muzzle gases and traps them during the process. It can also be observed that the muzzle gases do not exit the suppressor until long after they have slowed and expanded. Additionally, the presence of a back pressure that is expected from suppressors is present at the inlet to the suppressor, indicating that it has slowed the muzzle gases. From these observations, it can be concluded that the suppressor would be effective for use on 300 blackout chambered firearms. However, to further verify this claim and quantify the sound reduction capability, an analysis using a much finer mesh that incorporates acoustic modeling, combustion effects, and the presence of a bullet traveling through the suppressor should be conducted.